Hello everyone, my name is Huang Yuhan and I'm going to present my research topic about the DC and DC bidirectional converter control. And my advisor professor is the陳鴻祺教授. To start with, we have four outlines here. The first one, the abstract. The second one is the introduction, and next to the implementation, the results. And last one, we'll explain about the summary. Okay, start with this abstract. In this experiment, I'm using the TL494 pulse width modulation PMW processor paired with an IR2111K driver to analyze the bidirectional power flow characteristics. The system's performance is empirically evaluated under transient transitions, steady state loading, and reverse power generative modes, establishing a foundation for higher efficiency energy storage interfaces. So we have three objectives here. The first one, the characterization of and the analysis. The second one is the closed loop feedback loop design. Last one is bidirectional power flow operation. So we get into the introduction. So start with the circuit places an inductor between the low voltage DC terminal V battery and the midpoint node of the half bridge power states, comprising two series connected IGBTs or power MOSFETs. A high capacity stabilization decoupling capacitor CDC is placed across the high voltage DC link terminal VDC to attenuate high frequency switching voltage ripple. After the control signal V control is compared with the triangular wave signal, the comparator output signal is used as the lower arm switch signal G negative, and after the inversion, it becomes the upper arm switch signal G positive. The control voltage generated by processing core is continuously modulated against an internal high frequency periodic triangular carrier wave. When V control is higher than the triangular wave, the lower switch QB receives a high drive signal G negative, forcing it into the conduction. Conversely, when the V control is lower than the triangular wave signal, the lower switch is deactivated and the upper switch QA is driven on the G positive. And here we have two modes in this circuit. The first one is the boost mode or the discharging mode. In this boost mode, the buck-on boost converter can be used as a step-up converter in its boost mode. The output voltage here is higher than the input voltage. The converter achieves this by reversing the polarity of the input voltage and drawing power from an energy reservoir, which is the inductor. So in this case, when it's in the boost mode, we have the first case we have the G positive MOSFET is off and the G negative MOSFET is on. In this case, the battery will charge the voltage through the inductor and goes through the G negative. When the pulse it goes through the inductor and goes back to the battery, the voltage in the inductor will have the same voltage as the V battery. And when the time switching goes to G positive is on and G negative is off, the voltage stored in the inductor will go pulse into the G positive pass through and goes to the V load, where the V battery will still goes to the V load, the inductor flow, the inductor here. In this case, as I said, the G positive is on and G negative is off, the V control will be higher than the triangular wave. And we have the second mode, which is the buck mode or the charging mode. In buck-on boost converter functions, it functions as a step-down converter while it is in the buck mode. It denotes a lower output voltage than the input voltage. The converter does this by relating the switch duty cycle to minus the average output voltage. So when the G positive is on and G negative is off, the load with the current from the VDC or the V load will charges through the MOSFET positive G, goes to the inductor and will store the energy here, the voltage here, and goes to charge the battery. So when it switches into the G positive is off and G negative is on, the stored energy to pass through the inductor will still go to charge the battery, whereas it will loop through the G negative. In this case, the V control is higher than the triangular wave. And here we have the derivation of the VSB. What is the VSB? We apply the principle of the inductor full second balance, VSB, across a complete periodic steady state switching equals TS times signal. The integral and of the instantaneous inductor voltage must resolve identically to 0. Let the lower switch conduction duty be explicitly denoted as the V control. The corresponding upper switch duty fraction behaves complementarily as the 1 minus the V control. So here we have the equation, the formula of inductor voltage equals the battery voltage times V control, and with the V battery minus VDC times 1 minus the V control. So in this formula, we have the V battery times the V control is the positive pulse, the positive voltage, and the 1 minus V control is the complementary voltage, which is the reverse from the positive pulse. The positive adding with the negative pulse will equals to the 0 pulse voltage. And by after simplifying the voltage here, the equation here, we got the VL equals the battery, V battery minus the VDC times add with the VDC times the V control. We can also use the back and boost converter in the continuous current mode CCM here, where the waveform here can define the duty cycle. We have the VL here, which is the when it's positive, it goes to the VD, the V diode, and when it's negative, it goes to the negative of the output voltage. And the waveform here is the inductor current waveform, which appears supposed to be in the triangle wave signal. Here we have the voltage output divided by the diode voltage equals to the duty cycle divided by the 1 minus duty cycle. And here is the more detailed waveform equation for the current voltage gain. We call it appears in the steady state because when the voltage is off and the voltage is on, we can see the continuous duty cycle and switching duty cycle, where the off duty cycle is equal to 1 minus d times the switching time, and the positive on is the duty cycle times the switching frequency itself. And we also can derive the current here. The current equation kind of equals to the output current divided by the diode current equals to the inverse of the voltage equation, which is 1 minus d divided by d. In this case, we'll assume that the power flow from the diode to the output flow is the same. It's equal. We got into the implementation of our circuit itself. So in this case, the TL494 is responsible for generating a variable with pools that control output voltage or current. The TL494's internal transistors cannot supply enough current to quickly charge and discharge the large capacitance of the MOSFETs. So in this case, we have the IR2111 step in. The combination of these two circuits, TL494 and IR2111, is a classic and very highly effective control scheme for our half-bridge power converters. The TL494 generates the PWM and the signal, and the IR2111 translates the HO and LO, which is the high side power and the low side power MOSFETs. The high voltage link feedback instruction relies on the isolated scaling resistive divider network. The high voltage potential VDC maps through the series 39K ohm upper series pad interacting with the 8.2 kilo ohm ground with the clamp resistor. The steady state feedback scaling ratio can be defined as beta equals to the ground clamp resistor divided by the series pad, the 39 kilo ohm, and with the 8.2 kilo ohm resistor. And finally, we can get the feedback ratio equals to 0.1737. By getting this feedback ratio, we can also calculate the feedback voltage, which is equal to the output voltage times the feedback ratio. Here's the more detailed implementation of our circuit. Here's the battery, the V battery, and here's the power supply or the V load of our experiment. And there is the circuit for our deciding on the breadboard that's with T494 and IR2111. Here's the A node and N node connected to the ground. Okay, so the power stage consists of two synchronously controlled N-channel MOSFETs, the QA and QB, connected around a common switching node A. QA operates as a low-side switch and primarily controls the inductor charging interval, whereas QB operates the high-side synchronous switch responsible for energy transfer to the output side. During the boost operation, QA stores energy in the inductor and QB releases the stored energy to the output capacitor. During the buck operation, the energy flows reverse and QB becomes the primary energy transfer switch. The IR2111 gate driver provides complementary high side and low side gate signals, enabling efficient bidirectional power conversion while minimizing the conduction loss compared with the diode-based implementations. The resulting switching node voltage and the inductor voltage are inherently complementary, explaining the experiment observing further waveforms. Here's the real-life implementation of our circuit, and this is the battery, car battery here. Here, we connect it to the power supply from the TV load. In this case, when we connect the heavy loads, for example, the 30 kilo ohm resistor to the high voltage side, the converter has to pull a massive amount of current from the low voltage side to keep the system running. During transitions of the heavy loading, a single channel operating independently cannot provide enough current, causing the power supply to shut off. So with the parallel mode here guarantees that the power supply can handle these high current spikes better. Here is our output voltage to the V load. We have the multimeter to calculate the V battery, which is equal to, I calculated 12.01 voltage, and we have the duty cycles equals close to 53.3%. So we have the back equation as the buck and boost converter. Formulas we get the V out equals to the duty cycle times the VH. V out is close to 26 volt, and the boost mode we have the VO equal to V in divided by the 1 minus duty cycle. Also we get the V out close to the 26 volt. And here's the result. In the buck mode, we got here there's we have 4 channels here. The first one the inductor current, second one the INAT. The INAT is the current from the gate MOSFET, and here's the channel 3 is the inductor voltage. The channel 4 is the VAN voltage from the node A to node N from the previous implementation. We have our current in the inductor current appears in the steady state and in a triangular way, because here we have the equation of the derivative of the current inductor current equals to the V battery divided by the inductance. So when the current is higher than 0, it will ramp up simultaneously in the constant slope, and when it's lower than 0, it will ramp down back to the origin. And the INAT is controlled by the MOSFET B when we have the state where when the QB is on, the current will flow, and when its QB is off, the current will not flow. And at times with the inductor voltage from here, we get when the VL is on, the current will not generate the voltage, the waveform. But when the QB is on, it will pulse a triangular wave as it appears from the inductor current here. And in the buck mode, we had the battery charger. So here in the power supply, we also increase the current to 0.5, 1.5, the limit is 2. I do this simultaneously. And as I increase the current to the higher current from the V load, the battery charges faster, and the current from the for the inductor current will ramp up simultaneously. So we can see here the voltage will getting higher, the current will getting higher, and the ground will be further from the waveform. And as I said, the channel 3 is the VL. The VL has the VL equals the V battery, which is impulsing when the positive, here's the ground, is positive, and when it is V battery minus V out, the VL will be appears in negative, so it drops to the negative voltage and will appears in steady state. And when it's channel 4, the VA, the VL is equals to VL equals to the VL add with the V battery here. But when it controls by the MOSFET, when the QA is on, it's 0, so it's off. There's no impulse. But when the QB is on, the MOSFET B is on, it will generate the V out signal. So that's why it is inverted with the voltage from the inductor. So as a summary, we had the operating mode of the bidirectional buck converter is determined by the direction of the power transfer and the voltage conversion relationship. When electrical energy flows from the high voltage to the low voltage battery, then the input voltage, the converter will operate in the buck mode. But conversely, when the energy is transferred from the battery to the V load, the output voltage will sees the input voltage, and the converter will operate in the boost mode. The operating mode may also be identified by controlled by the PWM switch and the switching node waveform, since the switches are actively modulated in buck and boost operation. So that's all. Thank you for hearing my presentation here.